Hello everyone. In today's video, we're going to discuss about ResNet architecture. Introduction. After the first CNN-based architecture, AlexNet, that win the ImageNet 2012 competition, every subsequent winning architecture uses more layers in a deep neural network to reduce the error rate. This works for less number of layers, but when we increase the number of layers, there is a common problem in deep learning associated with that called the vanishing or exploding gradient. This causes the gradient to become zero or too large. Thus, when we increase number of layers, the training and test error rate also increases. In the above plot, we can observe that a 56-layer CNN gives more error rate on both training and testing dataset than a 20-layer CNN architecture. After analyzing more on error rate, the authors were able to reach conclusion that it is caused by vanishing or exploding gradient. ResNet, which was proposed in 2015 by researchers at Microsoft Research, introduced a new architecture called residual network. Residual network. In order to solve the problem of the vanishing or exploding gradient, this architecture introduced the concept called residual blocks. In this network, we use a technique called skip connections. The skip connection connects activations of a layer to further layers by skipping some layers in between. This forms a residual block. ResNets are made by stacking these residual blocks together. The approach behind this network is instead of layers learning the underlying mapping, we allow the network to fit the residual mapping. So instead of say h of x initial mapping, let the network fit. The advantage of adding this type of skip connection is that if any layer hurt the performance of architecture, then it will be skipped by regularization. So this results in training a very deep neural network without the problems caused by vanishing or exploding gradient. The authors of the paper experimented on 100 to 1000 layers of the CIFAR 10 dataset. There is a similar approach called highway networks. These networks also use skip connection. Similar to LSTM, these skip connections also use parametric gates. These gates determine how much information passes through the skip connection. This architecture, however, has not provided accuracy better than ResNet architecture. Network architecture. The network uses a 34-layer plain network architecture inspired by VGG19 in which the shortcut connection is added. The shortcut connections then convert the architecture into a residual network. Implementation. Using the TensorFlow and Keras API, we can design ResNet architecture including residual blocks from scratch. The implementation of different ResNet architecture. For this implementation, we use the CIFAR dataset. The dataset contains 60,000 32 cross 32 color images in 10 different classes: airplanes, cars, birds, cats, deer, dogs, frogs, horses, ships, and trucks, etc. This dataset can be accessed from keras.datasets API function. Step 1. First, we import the Keras module and its API. These API help in building the architecture of the ResNet model. Now we set different hyperparameters that are required for ResNet architecture. We also did some pre-processing on our dataset to prepare it for training. Step 3. In this step, we set the learning rate according to the number of approaches. As the number of approaches, the training rate must be decreased to ensure better learning. Step 4. Define basic ResNet building block that can be used for defining the ResNet V1 and V2 architecture. Define ResNet V1 architecture that is based on the ResNet building block. Define ResNet V2 architecture that is based on the ResNet building block as well. Step 7. Train and test the ResNet V1 and V2 architecture. Results on the image dataset, the authors use a 152-layer ResNet, which is 8 times more deep than VGG19 but still have less parameters. An ensemble of these ResNets generated an error of only 3.7% on ImageNet set. The result which won ILSVRC 2015 competition. On COCO object detection dataset, it also generates a 28% relative improvement due to its very deep representation. The result shows that shortcut connections would be able to solve the problem caused by increasing the layers, because as we increase layers from 18 to 34, the error rate on ImageNet validation set also decreases, unlike the plain network. Below are the results on ImageNet test set. The 3.57% top error rate of ResNet was the lowest, and thus ResNet architecture came first in ImageNet classification challenge in 2015. Architectural innovations. ResNet's architecture introduces identity mapping and bottleneck design to enhance network performance. The use of patch normalization and skip connections further contributes to its efficiency and robustness. ResNet variants. Various variants of ResNet, such as ResNet XT and Wide ResNet, have further extended its capabilities. These adaptations address specific challenges, expanding ResNet's applicability across diverse domains. Training efficiency. ResNet's architecture facilitates faster convergence during training, enabling efficient optimization. The use of skip connections mitigates the vanishing gradient problem, resulting in accelerated learning and improved model convergence. Challenges and limitations. Despite its remarkable performance, ResNet architecture faces challenges related to computational complexity and memory requirements. Addressing these limitations is crucial for broader adoption and scalability. Applications across domains. ResNet's versatility extends beyond image recognition, finding applications in natural language processing, medical imaging, and autonomous systems. Its adaptable architecture has catalyzed advancements in diverse fields. Future prospects. The future of ResNet architecture holds promise for further advancements in deep learning. Ongoing research aims to address its limitations and enhance its adaptability, paving the way for unprecedented breakthroughs. Conclusion. In conclusion, the exploration of ResNet architecture has unveiled its profound impact on the realm of deep learning. Its innovative design, superior performance, and diverse applications position it as a cornerstone in the evolution of neural networks. Thank you.